Hey guys, welcome to your Unit 1, Lesson 4 Notes, Adding and Subtracting Radical Expressions. Remember that a radical expression is something with a radical symbol in it. So, today you will be able to add and subtract radical expressions. Let's do a quick review with addition and subtraction before we go on. So look at my very first one. We have 5x plus 3x. And you'll notice that they have something in common. They, again, I'm using the wrong tool for my radical notes. They both have an x in common. And without going too much into their dating history, get it? Having an x in common. We call these guys like terms. So because they both have an x, we can pull that x out and see what's left. So we have 5 plus 3x. We're undoing the distributive property here. Excuse me. 5 plus 3 is 8. So you have 8x is your final answer. Think of it this way. Think of it as you have, boxes. You have a stack of 5 boxes over here, and then you have a stack of 3 boxes over here. How many boxes do you have total? You have 8 boxes. It doesn't matter what's inside your box. We don't need to know what's inside our box. As long as we know they are all boxes, they are all X boxes, no pun intended, we have 8 of them. This is the idea we're going to use all day today. Going over here. Now instead of X boxes, we have Y boxes. So we've got some Y boxes over here. We want to figure out how many Y boxes are we left with. We can pull a Y out of each of these guys, leaving us with just 8 minus 2. 8 minus 2 is 6. So we have 6Y, and that's our final answer. Again, the process is like we have a stack of 8 Y boxes, and we're going to take away 2 of those Y boxes. What do we have now? Well, we have 6 Y boxes. And now we're putting our X boxes and our Y boxes all in the same place. We've got some Y boxes to deal with over here. We've got some X boxes to deal with out front. So we can combine like terms and we can clean this guy up. So that gives us 7 plus 2X boxes. And then be very, very careful. It's not minus 8 plus 5Y boxes. Instead, think of this like plus a minus 8Y. So instead, we have a plus here and we have a minus 8 right there. Okay. So cleaning up our like terms, cleaning up our X and Y boxes, we are left with 9 X boxes and negative 3 Y boxes. So we can leave it like that, that's fine, or we can say that's 9x minus 3y, and that works as well. So we're going to use the same concept, but with radical expressions. So our idea here is we're going to use the distributive property. I don't know why it's such a long word, but there you go. The distributive property to add and subtract radical expressions. Just like up here, we undid the distributive property by taking the x out of the expression. And up here, we undid the distributive property by taking the y out of the expression. We're going to do the exact same thing. So here, we open up our x boxes, and we discover that inside of our x boxes, oh, it's a square root of 10. This is actually a square root of 10 box. So let's factor out our square root of 10. That leaves us with something square root of 10 outside. After we take the square root of 10, after each of our guys, we have 5 plus 3 left over, which is a total of 8. So we have 8 times the square root of 10. There, it's all simplified. So 3 square root of 10 boxes plus, 5 square root of 10 boxes plus 3 square root of 10 boxes leaves us with 8 square root of 10 boxes. So we undistribute the square root of 10. Undistribute. I don't know if that's a real word, but it is now. So what should we do for our second go around? Why, we should do the same thing. We should undistribute, but this time instead of undistributing the square root of 10, we're going to undistribute the square root of 3 because they both have a square root of 3 in common. So we're going to pull that square root of 3 out from both expressions, from both terms, and we're left with 8 minus 2. Last time I checked, 8 minus 2 is 6. So we get 6 times the square root of 3, which is much more simple. Okay? Right. Now, let's talk about like and unlike terms. You'll remember from talking about radical expressions, when you have a radical expression, the thing underneath the radical, let's say if you're like 52, for example, the thing underneath the radical we call the radicand. That's what I mean. The thing, the number, the expression that's underneath the radical is called the radicand. We're going to put the can in radicand today because you can do it. So a like radical is when you have radicals, like radicals are radicals, yeah, with the same radicand. So guess what an unlike radical is? An unlike radical is a radical with a different radicand. So if we have, for example, oh yeah, these are unlike. Wrong tool. Unlike. So pair of like radicands would be like 5 times the square root of 2 and 8 times the square root of 2. They are like radicals because their radicands are the same. We both have square root of 2. However, if you have 5 times the square root of 2 and 2 times the square root of 5, those are unlike radicals because what's underneath the radical is different. Those are not the same. So now that we have all of our terms, we are going to we're going to add and subtract radical expressions. So what we're going to do first is we are going to simplify each radical expression best as we can. We're going to look at what we have, we're going to clean up our ideas, make it as simple as we can. And then from there we will combine like radicals. We'll take radicals with the same radicand and combine them together. We have 2 examples. Our first example is 4 times the square root of 27 minus 5 times the square root of 12. So first, let's simplify each radical expression separately. So I'm going to do this by working on 2 factor trees. First, I'm going to factor 27. So 27, I can split into 9 and 3. Ooh, this 9 is going to be very helpful because 9 is a perfect square. 9, in fact, is 3 times 3. So that's really nice. 9 is 3 squared. So in doing so, this is equal to 4 times, instead of the square root of 27, we're going to say 4 times 4 times the square root of 9 times 3. So we can split that up even more. Square root of 9, square root of 3. And the square root of 9 is 3. Awesome. So it gives us 4 times 3. Nope, I wrote that wrong. 4 times 3 times the square root of 3. And 4 times 3 is 12, so we have 4 times this. I wrote it right and I said it wrong. 12 times the square root of 3. So we cleaned up the first half. Awesome. Now let's clean up the second half. Okay. The square root of 12. Well, let's factor out 12 and see what we get. So to create a factor tree of 12, 12 is 3 times 4, and 4 is, I need a different yellow for this, don't I? 4 is 2 squared. It's 2 times 2. So that's nice. Because we found a perfect square, we can factor it out. So we're going to rewrite this. Instead of taking 12, we're going to write 4 times 3. So we have 5 times the square root of 4 times the square root of 3. And like we just found out, the square root of 4 is the same thing as 2. So we have 5 times 2 times the square root of 3. 5 times 2 is 10. 10 times the square root of 3. Wow! Now I know that it looks like it's the same simplification. We have two radicals. But guys, we can clean this up even more. Do you see what they have in common? They are like radicals. They both have a square root of 3. So we're going to undistribute that square root of 3. And what we're left with is 12 minus 10. 12 minus 10 is 2. So our final answer is 2 times the square root of 3. And that's it. And that's so nice. Turns out this whole expression is just equal to 2 rad 3. Great. One more. Man, these numbers have like nothing in common. What shall we do first? Let's simplify the radical expression. So let's work with 18 first, and we'll make a factor tree of 18. And 18 is, you know what, let's do 6 times 3. 18 is 6 times 3, and that's not very helpful because we don't have a perfect square yet. But 6 is 2 times 3. Oh, nice. So because we know that 18 is 2 times 3 times 3, 3 times 3 is 9. So that's 2 times 9. And what's nice about 9 is a perfect square. 9 is 3 squared. So we're going to split 18 into 2 times 9. So even though we didn't split it into a perfect square right away, we eventually found one, which is nice. Okay? So we'll keep splitting it up. 7 times the square root of 2 times the square root of 9. And remember, the square root of 9 is 3. Awesome. I'm going to rearrange this just a little bit because it helps us with our math. So that's the same thing as 7 times 3 times the square root of 2. 7 times 3 is 21. So that's as much as we can clean that guy up right there. Let's do the second half. Square root of 50. Well, let's go ahead and factor 50. Go purple. Man, I didn't do any of this in pink. Oh well, I will clean this up. I will make this pink for the notes key so that you can see it matches. Alright, 50. Let's split 50 up. 50 is 5 times 10. That's real easy. 5 we can't split up anymore. But 10 we can do 2 and 5. So 50 is 2 times 5 times 5. And 5 squared is 25. So we can also rewrite 50 as 2 times 25 because 25 is 5 squared. So that's going to be much nicer. Okay, so we have 3 times, instead of the square root of 50, 2 times 25. In fact, let's do 25 times 2. It's going to make our lives just that much easier. So we can split this radical up. 3 times the square root of 25 times the square root of 2. And like we just found out, the square root of 25 is in fact 5. So we have 3 times 5 times the square root of 2, and 3 times 5 is 15. 15 times the square root of 2. And we did that in one step faster, so we're just going to rewrite it for our last step. So we are here, and we have like radicals. We have the square root of 2 and the square root of 2. So we can undistribute that square root of 2, and we are left with 21 plus 15 together times the square root of 2. 21 plus 15 is 36. We multiply that all together by the square root of 2. And you guys, that is much, much, much more simple than our original expression. Wasn't that so great? So great. So remember, you need to combine like radicals, which have the same thing under the radical sign, and then you're done. So simplify them and then combine like radicals. I hope you have a fantastic time on your homework.